I gave this talk at a workshop at CVPR, it's updated, and I asked my neighbors sitting here, you haven't seen this thing at CVPR, and sort of nodded, so hopefully he's the only one who will have a repeat. I did change some things, but hopefully you like it. So actually, this is a workshop about deep methods. I think something like that is in the title, no? And in some sense, the correspondences are one of those places where still the deep methods have not completely dominated. And this is not that I would like to invite the onslaught of the people who do nets on everything, but I would like to review the situation. Are the classical methods dead or not yet? And if they are not dead, we actually is there death imminent? And I will put this into context in the lessons learned from image matching workshop challenge, which was done at CVPR, where some sort of fairly large, not large scale, like on data which probably would not allow full overfitting, some comparison of deep methods and classical methods happened. So we have fresh evidence on this subject. Now, so some people say that more or less they are expecting that the deep methods will overtake everything which has been done in even in the area of two-view matching and geometry and inference of geometric models. Now, so the correspondence is an old problem. Maybe you don't need to know that much about it, but you wonder why the hell, and I ask my students, why the hell in which year did they do stereo imaging? So 1860s, because the matcher was in your head. So they would take two images, and then the matcher was the human visual system. And actually stereo matching on registered images was probably one of the first successes of computer vision. So we have young guys here, and I am in the position to say something about history. So this type of matching, where you would have an epipolar line, which would be just a horizontal line, and a window that would find the disparities and reconstruct the 3D, appeared in early 90s, and it worked. Now, when I speak about correspondence problems, probably you think about this problem, which is maybe attracting 95% of all the papers. Given images and A and B, find a geometric model linking them. So most people don't even think about any other problem, but of course implicit in that task is that you assume that such model exists, and these two things depict related or overlapping scenes. I mean by related, you can have things like many years back I would say that if the scenes which are image in A and B are not overlapping, you can't match them, but it's not true. If you look at two images of a football stadium, you can infer from things like seeing parts of the central circle and some lines, the geometry as well. So the other problems, and I guess there are lots of young guys here, are, for instance, estimate reliably the confidence that the model is correct. Actually, this is an open problem. And in standard SFM, is there anyone who's doing structure for motion here, this type of thing? So these guys would say, well, okay. If I incorrectly match some image, I will get a false structure. So that's usually quite bad. So I'll say if I have 25 matches, this is good enough. It's quite reliable, and they don't try to scientifically somehow address this problem. If you are doing things like SFM these days, you probably crawl hundreds of, maybe thousands or tens of thousands of images, and actually maybe more, like before this, you are solving this problem. Can you establish that A and B have nothing in common very, very fast? Because if you take any images as an input to the reconstruction, you do not want to do this n squared times. You would like to do this on a small subset. Yeah? And okay, there's the problem of registration. So I'm saying that maybe deep nets are attacking this, and I'll talk about that. But these problems, like is the confidence in the solution, can I just reject the fact that I should not be doing this because this will cost me a lot of computational time? Can I do this? And how do I do set of an images? So for instance, it's quite realistic that if you have, maybe you have n images and you don't want to compute all pairwise relationships, it's enough to have a spanning tree there at the beginning. And running, for instance, many Ransacks in parallel have this nice idea that the simple problems finish first and then you terminate the ones which are very difficult. So this is not the same problem as do all and choose two pairs. Now, in around 2000, people moved from that very nice setup where the Lincoln image with the two cameras was same illumination, exactly the same instant. You can assume that the intensities were, in corresponding pixels, were the same, to white baseline, where this was taken at different times of day. It took me sometimes to move along the Chinese wall from one place I took these images, to large scale changes. And this required new techniques, and lots of people worked about it. And let's say, we can say that the SIF method of Low, which was developed around 2000, became let's say the dominant thing in vision. It was one of the other things that started to work in vision. This paper itself had so many citations that it increased the impact factor of IJC by 2. And in around 2010, maybe people moved also from wide baseline in terms of geometry to wide baseline in other things. Here modality, this is infrared against visible, some historical, so wide temporal baseline in the time the images were taken, very different illumination, very extreme viewpoint. So this is all now in wide baseline stereo, and this type of problems can be dealt with. Of course, here I have examples where sort of one dimension has a wide baseline, and of course all of these things can happen at the same time. I'm looking at the same building at night from a different viewpoint. And that, of course, increases the challenge. So, how does the standard approach look like? The classical one that worked and actually is running in the, let's call Colmap the standard structure for motion, open source solution that anyone of you can use. So, we start with two images, which say, let's say, assume they can be matched. Usually we get some detectors. We'd say, well, okay, there are some points which I can detect repeatedly, regardless of the illumination and the viewpoint changes. Then their neighborhoods are described. There is some matching procedure. That matching procedure produces something I call tentative correspondences. And I have Andrea Vedaldi here from Oxford. The Oxford people say putative. No matter how many dictionaries of English I study, I think putative is wrong.
I don't say that. Why do you say that? I say that.
Putative is something that we pose like a hypothesis, like unfounded assumption. Tentative is something that we consider correct for the time being, unless other information comes into the game. So putative would be like, okay, so that's how I understand, but who am I to tell the Oxford people what to say? But if they're Italian, I may. Now, there are other things that can be done and has been done, which most of the pipelines don't have, like for instance the Colmap one. For instance, if you want to match extreme viewpoints, it does help to synthesize some warps of the input, and you might hope that one of your synthesized guessed, this time I would say putative warp, will be close to the other one, and the matching will work. But in some sense, why is it not used? Because the SFM people usually take quite a dense coverage of the scene, and they would not spend ages trying to match very difficult views. So the question is, do we ever need this? Like usually in SFM, your point is to change the unordered set into things which are from similar viewpoint, and not to do the extreme viewpoint. The other things that you could do is like, you can improve your correspondence verification, because this matching has to be based on something that is not quadratic in the number of, the number of points in one image times the number of points in the other image. So you use something like hashing on nearest neighbors, but once you have a matching and verification, I'll speak about this later. You can do things like guided matching. Once I have the model, I can go back somewhere far at the beginning and densify. Yeah? So it's not clear at the moment, but until, I would say, last 2 years, when the call map or the SFM structures became available in open source, people who did matching would be too much concerned about how to insert this in bigger systems. We would say, okay, if we have the epipolar geometry, we have done well, and that's what we need. Okay. Now, these days, various parts of that pipeline are being replaced, or you have suggested replacements. So I chose Superpoint as something that is in some sense very simple. So you say, well, okay, if I have 2 images, I can run some net, it will give me some interest points and also some descriptors, points and descriptors, and I can match that. So this would keep the matching and Ransack outside of that. Of course, there are many options how to do that. What should be the structure of the network? What should be the cost function? What should be the points that I'm trying to find in the two? Best of all, maybe I don't even want to say what these points are, that they will come out of the learning process. So notice this is only the front end of the pipeline. So the matching part is still the classical thing. People present much more complex ideas. I think this is crazily complex for the thing, but you get points, you do the local description, global description, lots of complicated things, and then you get 2% improvement, and this was an oral at CDPR. Yeah. Okay, let's see how it goes. And now, and this happened in the last 2 years. This is wrong. This should have been 18. People try to do end-to-end from the images to features and positions and some sort of regression or estimation of the fundamental matrix. So sort of removing the Ransack part. And I was very skeptical about that. I'm sort of changing my mind in the sense that it turns out that you could perhaps robustly estimate F as iterated reweighted least squares where the weights are coming from, are estimated on the correspondences by the network. Yeah? So it could be that iterated reweighted least squares is a very powerful method that avoids the sampling. Okay, so let's come back. I'll just say something about what is the state of the art in the classical method before we switch to the evaluation from the workshop to see how these deep methods and the classical methods compare. And that part was effectively only comparing this part of the pipeline, because I would say there is no established standard in the deep methods here. And also, it's very difficult if you want to test you cannot really understand much if you try to test everything at the same time, because you don't know where the problems come from. So I'll just show a couple of things which, okay, maybe this is what I want to say is that, okay, the deep guys will come and they will produce results where they will improve, but it will be my job to persuade them to compare with the state of the art in the classical methods. So, for instance, one idea of the correspondence verification, and I'm not sure whether the DeepNet can do something like this, is this. Imagine that this is in your database, and this is the patch that you are matching. Now, if you look at this area of the image, this cannot be distinguished. But if you look at the larger patch, it's easily distinguished. On the other hand, if you have two views of these branches, they're from different views because the background has changed. Maybe you need a much smaller patch to have a chance. So there has been some effort by Ferrari and us and so to do something like those segmentation, which says, okay, if you have a guess that this is a match, maybe you can grow the area that is in correspondence and verify. And if without this, these two omnidirectional views from winter and summer couldn't be matched, and with this technique they could be matched. So there's an iterative process involved. I wonder whether deep nets could somehow, maybe you can say, well, you have masking and all those sort of things. It would be, if the deep nets could do something like that, co-segmentation nets, I will be impressed, and it also means that they can do this sum inside the machinery. They will be able to match things where the matching part is non-compact. That's the point. Like most of the assumptions are, and test materials on buildings, where it is true that what is matching is some sort of compact region. This is not the case here. And the same thing could be happening in all sorts of like biological structures which are growing. Okay, so that's one thing. Now, a silly small improvement, which together beats some of the, with the other state-of-the-art things, beats the deep nets now still. It's an interesting thing that people haven't thought about. So, Low's matching approach is, which is the standard, is that you do this fast, but think about it this way, that for every descriptor in image 1, you try to find the nearest neighbor and the second nearest neighbor. And you say, well, I consider the match as reliable if the nearest descriptor, hopefully my correspondence, so something from here to there, is at least 0.8 times smaller than the second nearest neighbor. So the competitor is somehow giving you the reliability. But now, SIT has this property that on one point, it can give you up to 4 responses. And so, for instance, if you have symmetric situations like that, this match, which is correct, will be killed by the match which says exactly the same thing. This point is that thing, a point. But one has this orientation, the other one has the other orientation. And it's enough to say, okay, replace the second nearest with first geometric inconsistent. So we say, well, the competing match that will be giving me the ratio 0.8 will have to be somewhere else than on the matching point. This happens for different orientations, also depends on scale. So for instance, if you have a corner, then the corner like here is a well-defined point, but the scale might not be well-defined, so the detector might fire a number of times. You'll see that this gives me a couple of percentage points, and it's a trivial chain. The other thing where things can be improved is Ransack. So we have recently proposed 2 things in Ransack, which it's interesting they haven't been touched before. And the idea of this graph cut Ransack is this. If you take 2 points and you ask, is A and B both an inlier, both an outlier, or they have different labels, it's much more likely that nearby points have the same label. But already going all the way back to Gauss, you somehow consider the residuals as independent. So your cost function is a sum over terms which have only one point. If you take the binary thing into account, it turns out that a miracle happens, that Ransack works faster than you expect. Because these, like here, because of this binary thing, all of those points are considered correct, because it promotes, the graph cut promotes labeling nearby structures the same way, like in or out, and you get the correct answer fast. Now, it turns out that this thing, for instance, improves the results. You see, this is the geometric error by a significant factor. And actually, the speed is not influenced too much. The graph cut doesn't cost you much. And also, it's like for the given model, the graph cut for binary gives you the optimal solution. But there are more that can be done, and this is after 40 years of Ransack or whatever, 40, 82. Well, it will be, we'll have an anniversary in 3 years, I think, or 2 years. So people have fought with the idea, with the problem of where do we get the scale for Ransack. Now the answer is, what is the standard statistical approach to quantities that you don't know and you don't want? Marginalize over them. So there has been a string of work which says, I somehow estimate the scale, and then I use it as if it was the right scale. But we don't have to do that. Okay, we can go through a range of scales that will get them calculate their likelihood and marginalize. Things which, so with this, which was this here at CDPR, we improve the precision, like here it's like 56, 58, we use to 0.38. This error is in pixels on manually handpicked points with a student zooming out the image. I think that we are reaching, I don't trust that this thing is like, you can get any better because that must be the noise in the ground truth data. But for some other things, it's like from 5 to 1. So there is still space for improvement. But now we'll come back to Okay. The interesting thing why it works is also that people use this quadratic gloss, but if we are doing it for sums of quadratic errors, you should be using chi-square. So there is we had to fix that because of the marginalization. We need the likelihood of the model. Okay, so now what will be happening in this? What happened in the competition? Like I will focus on Hartnett, which is a sort of VGG-like net applied to the descriptor, and it seems to be now clearly superior to the safe descriptor. And the contest desk, which is that complex animal I showed you, let's think about it like non-transparent, huge box doing something but performing well. And also we'll compare with Superpoint and D2Net, which is a very interesting thing from this year's CDPR, where the authors have come up with an interesting cost function which promotes, let's say, they don't have to say what, they say what we want to find is an operator which gives us peaky response which is repeatable, and that's it, and they define it in a neat way. So I think I think the work on this will be improved, and work on that there will be some follow-up work. So this challenge was organized by Edward Rules and Kwan, and it's interesting because, as you will see, as we were doing this study and comparing it, we found out that they made, I would say, quite serious mistakes in the design of the challenge, and yet they provided us with all the data. So I think if we manage to do this in computer vision, we'll progress fast. Because like if you look at aircrafts and the whole industry, the safety thing has improved so much because they have a extremely good procedure of analyzing crashes and all sorts of near misses, and they have to do it in a way that everybody contributes. Like if the pilot is worried about the consequences, he will not tell you the full story. If you can arrange things that everybody does the post-mortem completely openly, a lot of information is revealed. Also, we are in a new situation that we have a well-performing structure for motion, which is 3D reconstruction pipeline, which all these things can be plugged into. So this gives the matching community a lot of options to generate ground truth data, modify protocols, and so on. So the challenge was made on a data set which was created from reconstructions. You see that for each of the views you had like 6 other views which were similar. From my point of view, these are nothing terrible, quite simple things to match. You verify these points using a 3D reconstruction, and okay, I think my slides for that. Because you know the reconstruction, you can have ground truth correspondences and validation of the models that come out of the process. So we now, and this can be now changed quite easily. So it's easy to benchmark. In principle, it's easy to benchmark whether certain matching detector and descriptor matches points and helps towards 3D reconstruction. So when the results came out, they were sort of shocking. So I'll try to explain the shocking part maybe here. So they took as a reference SIFT, which means detector SIFT, which means difference of Gaussian detector, then run this complicated descriptor, did the matching on 8,000 points, and now they were asking, like, I will not explain exactly what these things are, but they got the epipolar geometry from a pair, and because they knew the calibration, they said, okay, let's measure the percent. It's a map, but let's think about this as the percentage of images, pairs, which were within 5 degrees. 1 in 1,000. How many were within 20 degree error? 20%. You think, how could that happen? That for such easy pairs, the results were so bad. And then there was this was for the stereo problem. And now there was a multi-view stereo where you didn't get 2 images, you get many more. But actually, this is a mixture of these problems. And there, the result was 77% accurate. So and this is on this is on the leaderboard just before the day of the workshop. I think, how could that be? This was released very late. How could that be? And so first of all, how come all the methods perform so poorly for the stereo problem on such easy scenes? And how come it's so different that actually the multi-view stereos, you were given a batch of 6 images and you had to do all pair matching somehow. So more or less it's like these two things are asking about their same properties. And we look at the data. Wow, like this could have been matched in 1991. Yeah, what the hell is going on? So here a little bit more difficult, but still nice frontal views. Should be easy. Again, I don't know. How can you imagine this cannot be matched? Something is wrong. So how was this evaluation performed? Like competitors or participants, they provided features and possibly matching. They didn't have to, and then this was run through in the stereo. So you see, the task is almost the same from the point of view of tested algorithm, but the evaluation is quite different. One you run OpenCV Ransack, and the other one you run the call map Ransack plus bundle adjustment. You get the pose estimation, and you then check how far the views were to compute the map, to compute the score. So we thought that there must be some problem with the Ransacks here, and indeed. Now this is another thing. These days, we are in this new beautiful world where all the code is available, and we could look at GitHub, what they were doing, and it turns out that the matrix K was not normalized, and it was something in huge numbers. And when they were looking for the essential matrix, it turns out that they didn't rescale it, and in fact, it was operating. The method was operating. This is the result from the challenge, as if the threshold for inliers was set to 1/100th of a pixel. So almost no inliers survived. So we said, okay, let's see what happens with the results if we start increasing these pixels. Yeah? And the performance was going up like that. And if we go high enough, this is what we get, and very similar results are obtained for the two problems. Yeah? So this was some sequence OpenCV SIFT. So now SIFT goes from this performance to that performance, and now we can start looking at what happens with the deep net. So this was the result of the challenge. We discount that. We correct for this. So we reran the Ransack not with threshold 1/100th of a pixel, but with threshold 1, and OpenCV. So what they did, which is also sort of not, I'm not sure how they came up with that, but they said, okay, I will use every single point be input to Ransack. This means I will not use the ratio to select good matches. So you see that if you say every point has to have a match, your performance is crazy, but now this is the real baseline. Superpoint, which is nice, fast, and simple, deep, is worse. So it doesn't beat the classical thing. If we use the difference of Gaussian detector and use the context description, say complex deep net, we improve, we get the state of the art. But if we use the Hartnett, which was there as a baseline a couple of years, the difference is almost non-existent. So the result is that from this table that the performance of the new complex net is not really better than BGG, and as a detector, the SIFT is better than the Superpoint. And okay, Superpoint is very fast. That's another thing. It's very simple. Maybe it will be improved, but it's not yet there. Now, if we look at the what happens if you replace the second nearest neighbor with the first geometric inconsistent, you get to the improvement which beats the learned stuff for the context descriptor. Yeah, so this thing has one of the contributions of the paper is a new matcher, but actually it's worse than slightly modified second nearest ratio. Interestingly, for Superpoint, it works, and okay, it shows that, let's say this would be what people use this would be the classical pipeline. Sim descriptor. This is clearly inferior to what you can get now with the, let's say, BGG type of descriptors, and the second nearest ratio, if properly implemented with this considering geometry, is better than a learned method pushed in the paper as one of the contributions. And okay, what we try to do, like a lot of work has been done on affine invariance. So it turns out that with achieving making an affine invariant features, which is this one, almost no change, because the methods have no affine deformation. So these maybe instruction from Roshan, you don't need that. But the good thing is that if you try to have an affine features, it doesn't hurt you, so you can have it there as a safety net. So this is always good. Like if the affine invariance is not needed or covariance, it doesn't hurt me, and if it happens, I will be okay. Okay, so it turns out that Hessian and difference of Gaussians works the same. So fine. It means that in such large evaluation, it's not that important what classical interest point will be there. Okay, I'm not sure how much time I have.
You have a lot still now.
Sorry?
15 minutes.
Okay. So I'm not sure whether I want to spend. Okay, I could spend some time on this. So I will now talk about a couple of small things which make differences in the quality of a deep net trained solution. So one of the results was that the Hartnett, which is a BGG type, very simple descriptor, compares well with the context desk and the other complicated ones. And the only difference that we did in the Hartnett is we modified the triple loss. So this is the standard triple loss. What you do is that you take your batch will have an anchor. It will have a positive patch from the corresponding to the anchor, and then you will have many pairs, and these other images will serve as negative ones, as negative examples. You form a matrix where you measure the distance of everything to everything when you are training, and you would like you would like that the triplets which are in the batch satisfy this property that the anchor is closest to the patch, which is positive, than any of the other ones, and possibly with some margin. So this is here. So what you want, that this is the negative one, this is your one, and here you would like to have a margin at least 1 to have a zero error. But you do this for, actually these days you swap these row of these two for sure, and then you do this for every patch, and this is what you minimize over the batch. And now what people usually do, then you can minimize this cost with respect to the representation, like you can change the representation of your anchor, and you can also try to push away the negative one. And we said, well, forget about the derivative of this cost function with respect to the negative one. And I hope that it will work here for me. Okay, it's here. So if we look at the hard, so this is a visualization which shows the effect of changing the cost function when you are trying to design descriptors. So what you see here is like a two-dimensional descriptor, and the color codes what belongs together. So you would like to have something like this. The patch and the anchor corresponding together, and the whole thing far apart. So if you just say, I would like to have corresponding things near, you will end up, okay, the colored ones will be near, but nothing pushes these guys away from each other. Now, if you do hard negative loss, this is this one, so it says, okay, I want these to be near, far from each other, but look what happens here. These two are somehow fighting each other, and it takes a very long time before they sort of find a position, because what happens that you try this, you are trying. It's okay. I'll show the hard negative C result, and then I try to explain what's happening. So here we are saying, okay, we would like. You saw that it converged much faster, and here we are saying, I would like the same colors to be on top of each other, and the whole thing to be apart, far apart at the margin. But when we are optimizing with respect to some batch, we are only changing the position of the positive ones, not pushing the negative ones away, because we are saying the one that is the hard negative is a random one. Yeah? So, and this, when we were developing the Hartnett, this didn't converge nearly as fast as this, and actually we're fighting with this for a long time. Okay, so I would summarize the lessons learned from our submission is that still good and properly set Ransack is extremely important in terms of precision. If you don't use the ratio test, which the organizers of the benchmark didn't, you cannot get anything interesting. So you have to have a selector of matches which you use, and you have to have reasonably set up Ransack. Together, they were validated and they work well with the methods. Okay, learning. So this learning to match is not so far doing surprisingly much better than the second nearest neighbor, but maybe this is because the deep nets actually produce a nice space with nice metric properties that the nearest neighbor is good and the second nearest neighbor is a good estimate of the probability of the correct match. These days you have a very competitive and simple baseline and fast, where you say, well, okay, take some of these classical points, describe, and then you start they do the same, do the matching in a classical way. Now, it is true, for instance, that Superpoint is much faster than this. So maybe methods based on CNN will be doing everything up to Ransack, I guess, very soon, and it will be faster than any combination like that, especially if you don't work on batches. So the Superpoint uses the same feature pyramid or feature on for detector and descriptor. Okay, and then I'll just say that I would like to see in the next benchmark not only stuff related to SFM, but something much more challenging. So if you try to match that to one of the four, it's a difficult one, and I can ask you, not everybody sees that, so is this the matching one? Who thinks this is the matching one? No one. Is this the matching one? This? And that? Okay, so a lot more, I think the most common vote was I don't vote. And the second most common was this one. But this is difficult. So you will not see something in the benchmark like that, nowhere near. And the idea is that in the SFM matching, you actually, to discover whether this isn't really that, you need a lot of intermediate images. So on its own, it's very difficult to say this is that. But if you get intermediate images, this can be reliably matched to that, and this could be reliably matched to that, and this now relates to this in these chains, how certain I can be that this match is correct. So I would like to see problems where directly it's very difficult, but indirectly you can help yourself. So this shows that the problem of matching in a collection of images, like two images in the context of a collection, is different from just two images. I think that if you see this and that, we might guess, okay, I guess yes, but it's probably quite easy to generate quite a few images which would look in low resolution like that, and they would be different. But if you do this like almost tracking in scale, you can do that. And I would like to see, okay, so you were right. I would like to see things like extreme viewpoint changes. This thing is indeed somewhere here. But I think this is, and I know that because I have seen lots of intermediate views, but I think this is not doable, okay? So this is the extreme cases. We can go, again, extreme cases like this, and that. But unfortunately, this cannot be at the moment. This type of situation cannot be reconstructed. So what happens, unless, this is what the reconstruction people work on, if you give them a collection of images, which will have this and that, most likely you'll have two worlds. The day world and the night world, and it's very difficult to match. But that's why it's interesting to put it into benchmarks. You have extreme things like different specularities. So this thing is that thing. I think humans cannot say that. This is the extreme historical change. So this is something from it must be late 19th century. Also modalities. So this is also quite difficult, and putting it all together. So the benchmarks so far are sort of focusing on fairly narrow baseline, because in the large collections of images for the reconstruction, the images end up then to be of the same scale. Otherwise, they wouldn't have been matched in the reconstruction in the first place, and I wouldn't have had the ground truth. So there is a bias in these problems, which says, if I cannot match it when I do the SFM to generate ground truth, I will not be testing your algorithm on that. And occlusions, slow is occlusion. Again, this type of matching, I would like to see in the next challenge. I think we have one organizer of the workshop, so he might be the thing. Now, this is probably no more geometry anymore. And but deep nets are very good at this type of things. Like here, probably what is happening, you might have like, I think this one is infrared, near infrared. So there will be like transformational networks before you do the matching. So here I assume that the deep nets will bring a lot of, let's say, fast progress, because it turns people used to like match infrared to visible, but now you say, okay, predict, like you are predicting depth from the image, predict the visible if you have infrared, and this will work well. Predict an image if you have this type of a sketch. This type of things tend to work. And that's all I wanted to say.
Here's all time for questions. So,
Was it? It was 45 minutes?
it was up to 20 past, I think, in that time.
And that's 3 minutes.